Hello, welcome to video 35 in the lecture Advanced Mathematic Modeling. So we were looking at anomalous diffusion, where the mean square displacement increases as a power law of time with an exponent which is different than 1 over 2. And then we have looked at two possible explanations where this could come from. There, if we have our formula for the mean square displacement. So either in the first term we could have second moments which diverge, or we could have long-range correlations. And so I've shown you already some examples for long-range correlations. Now let's look at an example or the typical case of a random walk where the second moment diverges. And this brings us directly to Levy Flights. Where are they? Here, to Levy Flights. Okay, so what is a Levy Flight? Yeah. So Levy Flights are a typical type of random walk, and in the moment let us look at them only for one-dimensional in 1D, because very often they are analyzed in 2 dimensions, but let's for the moment keep it in 1 dimensions. So it's a one-dimensional random walk. And so we have a symmetric, so we don't want to have a bias, so we want basically that the increments, the expectation of the increments is 0, yeah. But we want to have the second moment should diverge, yeah. And so how can we get the second moment to diverge? So that's let's see. So how we set up the increments. So we say the increments ei, they are a product of 2 components. So we have I tilde times eta of I. So and this increment ei tilde. So that's just our normal diffusive thing. So we have increments with -1, +1, with equal probability, and basically these increments should give us a direction. Basically up or down. Later in a 2-dimensional random walk it will be the angle, so the compass direction the walker is moving. For here it just means up or down. And now if the etters would be 1, then this would be just our very normal random walk. And now the etter I, they are all positive. And they're taken now from a power law distribution. Taken from a distribution P of eta equals or proportional to eta to an exponent minus alpha. So that's our model for the Levy walk, and we have 2 contributions. So we have a sign. The sign is just random, plus or minus, uncorrelated in every step. And then we have here the length of the increment, so the length distribution, and the lengths are taken from a power law distribution. So how do I say it? So the step length taken from power law distribution. So let's look what you remember. So we will talk a lot about power laws distributions in the next video, but for the moment, so let's say that's so the length of such a step, and here we have the probability to have a certain step, and then we have seen for a power law we need a minimal step, and then we have a function which decays slowly to 0. And since if we wouldn't take the minimal step, we would go here to infinity, so we have a minimal step, and then here this decays as eta to minus alpha. And okay, so maybe let's write down some properties that we have. So first we need a minimal step length. Into 0. Yeah, so it doesn't matter, so you can take one. Basically that's just the scale of the whole thing. So that's the minimal step. And then, so like, what was the property of such a power law distribution? It means we will have many, if we take a random value now, we will very often take a value which is small, because like that's how the distribution looks. So we will often find many steps in this range here. Many steps are small. So mostly we will have small values, but sometimes we can have arbitrary large steps. And here it's important that we have a power law, that this is not an exponential, but because the exponential distribution would decay with a certain scale, and then larger steps than this scale would be very unlikely. But if we have here power law, so that means that very, very large step lengths eta might appear from time to time. So we have a minimal step length, and then we have most steps are very small, but very few, but rarely a very large step. So these are the three properties, and then of course the sign of the step is still random. Yeah. So the sign meaning from time to time the walker, so it goes either up or down. So how does such a walk look? And this I had already in the video before, but now we know where, in which case something like this appear. Let's say we start with this value here, and then typically we have small steps here, so like the walk will look like this. But then we can have suddenly a jump, yeah, a large rare jump, because then by chance we find a large value, so we have a large step length. So this could have been positive or minus, so in this case it was minus, so the walker went down. And then we continue. Now we have maybe small step, the larger but smaller step up, maybe another one up, another one down. Yeah. And then you see these jumps here, appear from time to time and in all scales. It's not that we only have large and only small, because we don't have here a step function. I mean, of course, we could have something which is a step function, so very high chance small steps, and then one typical value for large step. Yeah, this would maybe look also like this. So sometimes we have large and mostly small steps, but the trick is that here all step lengths appear with a certain probability, and there is no maximum. So like if you would, for example, have here a simple model, maybe I make this here in the corner, and let's say the distribution would be we would have here a small step, and so this would be P of eta, and then a large step with a small probability. Yeah, so you could think this could be the same. So most of the time small steps and sometimes a large, but this would give us a typical scale for the large step, and larger steps would not be possible. But in our power law, we can be arbitrarily large here. So it can be, if this is here some 5 centimeters, we could have a step which is some meters to the right. Yeah, so like in my graph here. So we could have jumped down to minus to very small value. Yeah? And we can also have, okay, we have some small steps here, some fluctuation, and then wow, we have something very big. Yeah, and so that's the typical walk that we have here. This rare big jumps, rare large jumps. So we have a catastrophe. And maybe now for the terminology, since I mean, so this is a random walk, but we call this a flight because we have these jumps here, and so this jumps means the walker suddenly he's not moving smoothly continuously, but he can jump. Here is like an animal which is hopping sometimes, then it's more or less walking again, but then it can hop. And this hopping kind of behavior, that's why the term flight is used. We also will see there is also other versions of Levy kind of random walks. There will also be Levy walks, and in Levy walk we don't have these jumps, but we will come to this. Now, I mean, this is a very simple kind of construction for such a random walk. Would this apply to anything? Okay, that's the question, because it's very simple. But if you look at natural example of time series, for example, the stock market, or which is the market at the price of our stocks at a certain time. Yeah, it's fluctuating always. Yeah, and then from time to time it can jump. It can jump because you have a major economic crisis, and then really you have a economic catastrophe. But it can also jump down because some political event happened. Or maybe it can jump up because, like here, we have the first company which can make a vaccine for corona, and suddenly some stocks jumped very largely because the companies are looking, or people looking very positively in the future, and then the value of all stocks is increasing suddenly, So there can be external influences from politics, from sport, or whatever. Which lead to such jumps, or it could be an inherent thing in such a system. So a crisis, a catastrophe in the whole system, which leads to large jumps. But if you would look only at a certain small scale, maybe the world would look harmless, because when you look on this small scale, you would say, oh, it's maybe even an anti-correlated random walk or something. It's very stationary, the x doesn't change so much. So if you would have only data for this amount of time, you would think, oh, we have a very stable financial system. Yeah. So this means like a short-term data, short-term observation might give a very wrong prediction about the behavior of the system in the long term. And so, I mean, even though stock markets don't look exactly like this, you don't have jumps so directly, maybe it goes a little bit more zigzag upwards or downwards, but still time series of stock markets, for example, and so on and so forth, can show behavior which looks like this. Yeah, but there could also be other time series of natural systems which have this kind of fluctuations. Yeah? And so the Levy flight is then a model to model this kind of unpredictability. So there is a kind of certain sense of unpredictability in such walks. So in the sense that if you have observation only for finite interval, for example this blue here, so this could give you a very wrong impression about the long-term behavior. Could very wrong impression about long-term behavior. So because like in the long term suddenly you will find the surprise. Yeah, here, so we have the surprise, and this surprise will also be there for the experts. So if for example you have the stock market, so where you can earn a lot of money, so you have a lot of experts who have their business in the stock market and will look at this time series every day and try to see what's happening, and they will know for every small increment up or down, they will know a reason and the economic reason, and they will say what's the financial situation of the moment. But or not uncommonly, these experts fail to see these large jumps because these jumps have an origin in processes which they don't see. Not necessarily, so the origin of these long jumps, these big jumps, are not necessarily the same origin of the small term behavior. Now the thing is, all our observations of course are short term. I mean, who of us has observations of more than some decades of data? Yeah, I mean, even our economy didn't exist so very long. Yeah, so there's a principal problems to have longer knowledge, longer term observations. But if the system is governed by such a process where the tails here of this distribution play a very important role, there can be surprises. And I would recommend you a book for this, The Black Swan, by Nassim Taleb. So that's an excellent book. So written in layman's terms, so like non-technical, where it explains about these kinds of behaviors and the surprises that you can have when when your expert knowledge suddenly fails here. And and he calls something like this sudden jump, which is totally unexpected, he calls a black swan. So this is here the the term which is now used by many people to describe this rare large jump here. I mean, so basically the processes which led to the divergence of the second moment here. So I mean, so these large jumps must be inherently there if this is the reason why we have anomalous diffusion. Yeah, and yeah, maybe so like he gives a very good example of this. So he speaks about the turkey. So that's the life of a turkey. That's time t. We have it's somewhere in the US. We'll see. We'll show you soon why. So like that's the life quality. And so the turkey starts, and he gets always good food, and life seems to wear very well. So turkey is growing in size, and he thinks, okay, my life is wonderful, and he makes an expectation, and then would say, okay, forever his life will increase a lot. And then suddenly we have Thanksgiving here, so we have the surprise. Thanksgiving, and the turkey ends up in the cooking pot. And okay, that's maybe it's a bit silly example, but it shows you that your expectation didn't include this rare event which you couldn't even predict, and so the prediction that the turkey had of his life suddenly was changed by a black swan. And now Nassim Taleb argues that in many systems, like in stock markets and in complex political systems, maybe even in climate systems, you have this kind of black swans, which then suddenly make predictions very, very large. Yeah? And now the question is, how could you figure out that something like this is going on? And we would be lucky if the increments follow really from a continuous distribution. Yeah? Because like if they really follow from a continuous distribution, and you would sample in the blue interval, so you would see samples from in this range, and you would see, okay, the distribution decays like something. But if this time interval is long enough, then maybe we would see, oh, there is a curvature. And if we would plot this distribution over a certain time on a log-log scale, then we would see, oh, at least at a certain time scale, this looks like a power law distribution, because like this p versus eta at a double logarithmic scale decays on a straight line. And then we might predict that if this is a power law, that these large jumps should be there. So a careful analysis with the methods that we're doing in this lecture here would help you, maybe even in such short periods which are rather quiet, yeah, to already detect the presence or the likelihood that we might have large jumps. Yeah? And so that's suddenly the modern applications of all this random walk theory and this power law diffusion processes, because we don't want to have the surprises in systems which govern the quality of our life, like the stock market or the climate or the political situation in countries, or yeah, and whatever, and that's why we are interested to see if we can really figure out already what's the signatures of some this large jumps. So basically the presence of super diffusion in our variable. Yeah? So we will come back later to Levy Flights. That's all I want to say in the moment about the Levy Flights, because what we now really should do, we should look first at these power law distributions. I mean, the power law distribution is not the only distribution which can lead to this kind of behavior. There's other distributions which have long tails of or fat tails and give rise to similar things. But maybe the power law is maybe the most paradigmatic distribution which leads to this. So let's now in the next videos look a little bit more on power law distributions. What are the properties? Where do they appear? They don't appear only as increments of random walks, they appear in many other systems. So what are the properties? In particular, does here the second moment really diverge? Because I didn't show you this yet. I mean, because only if the second moment diverges, we really have here super diffusion. And once we have discussed power law distributions in a bit more detail, then we will come back later to Levy flights and other walks with super diffusion. So we will make now in the lecture a kind of break, stop with the random walks for a little bit, look more careful on power law distributions, and then later come back to random walks. Okay, thank you.